In the previous class we looked at a brief introduction on hypersonic flows and what are their characteristics. Hypersonic flows are really high velocity flows, they are high Mach number flows, and they have some typical characteristics. One thing is that the flow kinetic energy v square by 2 is a significant fraction of the total enthalpy, that is H naught. Therefore, whenever there is changes in velocity, it produces large changes in temperature also. So, near stagnation points of bodies, very high temperatures are encountered. High temperature effects are important in hypersonic flow. The other aspect is that as Mach number increases, then the shocks come closer and closer to the body. So, at such high speeds as a hypersonic flow, the shock is really very close to the body. So, we get what are known as thin shock layers. It is so close to the body. Then the other sort of characteristics are with respect to thick boundary layers. Boundary layers become very thick, and as a consequence they may affect the inviscid flow also. And if you typically, because of the high temperature effects and high heat transfer in hypersonic flow, the way to minimize it is to go about having blunt shapes. Almost all hypersonic vehicles have blunt shapes, but blunt shape produces a bow shock of this nature. It is not attached but a detached shock, and this detached shock has a variation or a curvature of the shock produces entropy gradients along the streams or streamlines over here. So, from Crocos theorem we know that entropy gradients produce vorticity, therefore you get rotational flows and they form an entropy layer, and this affects the flow over the body. So, the entropy layer can go and wash over the body. We have various such physical effects like very high temperatures. As a consequence, you may have chemical reactions. Air as a simple mixture of nitrogen, oxygen and other gases may not remain the same. It may undergo chemical reactions, even ionization. So, when these physical features become very important, then we call the flow as hypersonic, which typically occurs for Mach numbers greater than 5. So, a good sort of ballpark number to call something as a hypersonic flow is Mach number greater than 5, but really these effects have to become dominant. Then we are in the hypersonic regime. Thus, I have in the previous class we discussed in detail. I just gave a brief review of that. Now, in this class what we would do is we have seen how complex the hypersonic flow or physical features in hypersonic flow are, but at the same time certain aspects like thin shock layers, shocks coming very close to the body, they produce certain and also high Mach numbers. They produce certain simplifications which also allow us to say extract estimates of the forces around bodies in hypersonic flow using relatively simpler theories rather than very complex theories. To get an understanding of this, let us just take the oblique shock in hypersonic flow. We know the oblique shock relation. So, you have the incoming flow and we know the shock turns the flow towards itself, and it turns by an angle theta, creates a shock of angle beta, and this is something we have discussed in great detail. And if you look at the oblique shock relations, P2 by P1 is 1 plus 2 gamma by gamma plus 1 m1 square sin square beta minus 1. Similarly, you have T2 by T1 and rho 2 by rho 1. Now let us take the limit. This is we are considering perfect gases in order to understand certain features of the flow. Let us try to understand what happens when Mach numbers become very high. So let us take this particular equation and let Mach number go large. So in that sense, when m1 square goes large, very high, then the term 1 has very little significance. So this has very little significance. So you can consider this to be 2 gamma by gamma plus 1 m1 square sin square beta. Even this one is very small. Okay, so you can produce a simplification of this kind, 2 gamma by gamma plus 1 m1 square sin square beta. On the other hand, if you take rho 2 by rho 1 and apply the condition that m1 square goes very large, we have two factors here, both in the numerator and the denominator. They become very large. Therefore, you get the equation that rho 2 by rho 1 is equal to gamma plus 1 by gamma minus 1. So the density ratio across an oblique shock goes towards finite values. As you increase Mach numbers, so density ratio approaches finite value, gamma plus 1 by gamma minus 1. Because of this, T2 by T1 is nothing but P2 by P1 by rho 2 by rho 1. So you can substitute that here, and a much simplified expression for T2 by T1 can be obtained. So as we put the limit that Mach numbers go to large values, then we are able to produce simplifications to oblique shock equations. Okay. So you can also consider the components of flow velocities parallel and perpendicular to the upstream flow. This is slightly different from the usual discussions where we consider parallel and perpendicular to the normal shock. Why this is done is most of the calculations for forces is with respect to free stream. Therefore, it is good to know what happens to velocities parallel and perpendicular to the free stream after the shock. This is just a transformation of the velocity vector into another coordinate system. So this can be accomplished, and again we apply the limit that Mach numbers go to very large values, m1 goes to infinity. So then we find that u2 by v1, that is the parallel component for the shock, it goes as 1 minus 2 sin square beta by gamma plus 1, and v2 by v1 goes as sin 2 beta by gamma plus 1. So the really good thing over here is that you are there is that explicit dependence on Mach number is getting removed. Of course, beta depends on Mach number, but soon we can see that as the Mach numbers increase clearly large, then even beta becomes somewhat independent of Mach number. Okay. So so what we see really here is that we are getting quantities which are becoming independent. Explicit dependence of Mach number is getting removed. Okay. So, always we are interested in finding out what is the pressure distribution over bodies. So, we want to know what is pressure coefficient, and pressure coefficient is determined as P2 minus P1, where P1 can be P infinity, which is the free stream conditions, by half rho u1 square v1 square equal to, so we can make this this should now be a standard transformation from half rho u square to 2 by gamma m1 square. You can do this by taking P1 out and then multiplying and dividing by gamma, P2 by P1 minus 1. So, in this equation we can apply P2 by P1 that we just obtained from the previous considerations. Then we get the equation 4 by gamma plus 1 sin square beta minus 1 by m square going to large values. This becomes 4 by gamma plus 1 sin square beta. So, again you can see that for coefficient of pressure also becomes explicit dependence on Mach number is removed here, but further if we consider the m theta beta relations for oblique shocks written here, tan theta is equal to 2 beta m1 square sin square beta minus 1 divided by m1 square gamma plus cos 2 beta plus 2. So, this expression, if you consider this and consider that we are having a hypersonic body, a body in hypersonic flow in the limit of large Mach numbers, also that it is a slender body. When we say slender body, the angles of the body are small. So, theta is small. So, if theta is small, we know as a consequence beta will also be small. Therefore, we can make these approximations. Sin beta is approximately equal to beta, cos 2 beta goes as 1, tan theta and sin theta both approximate as theta. And if you put those approximations into this equation, you get this particular result here, and then combine it with the fact that a Mach number is going to very high values, m1 tends to infinity, we get beta by theta is equal to gamma plus 1 by 2, or if you put gamma as 1.4, this becomes beta is 1.2 theta. That means beta is hardly 20% greater than theta. So, this is very much consistent with what we had discussed about thin shock layer. So, what we find here is that beta should be very close to theta. So, even if you look at this final discussion over here, at high Mach numbers beta also becomes independent of Mach number. Explicit dependence is not there. Okay, so what happens as a consequence of this? So, as a consequence of this, we find that in hypersonic flows certain theories that were developed very early on even by Isaac Newton, they are impact based theories for forces over bodies in fluid flow, where Newton considered that if you have a stream of fluid coming in velocity with the velocity u infinity, okay, and it impacts a body, let us take a flat plate kept at an angle theta, then the flow is suddenly turning to become tangential to this particular stream or particular wall, and therefore, if we do a control volume analysis around this body, assuming that all the velocity normal to this, or rather all the velocity just goes along the tangential direction, and the normal velocity just gets cancelled off. If we do such a calculation, then we can find out what is Cp, and the Cp is then 2 sine square theta. This was the expression that was given by Newton very long time ago, but this did not consider details of fluid flow, and now we know we are able in a position to plot the streamlines and find out what are the pressures around such bodies. But in hypersonic flow, for many reasons, including the fact that the shocks, they are very close to the body. So, if you consider what happens over here on a thin wedge placed in hypersonic flow, the hypersonic flow velocity u infinity goes across the shock and immediately it becomes tangential to the body, and this thin shock is occurring very close to the body. Therefore, we approach the assumptions that were initially taken by Newton quite some time ago. Therefore, we expect that Cp equal to 2 sine square theta will be a good approximation for the bodies in hypersonic flow. In fact, we can do it more rigorously also. In supersonic flow small perturbation theory, we saw Cp is 2 theta by square root of m infinity square minus 1, which simply stated that Cp depends on local surface inclination. The Newtonian theory also states that Cp depends only on the surface inclination. In the hypersonic limit, if we take a look at Cp, we find that it is actually depending on sine square beta, which we have just now done. And we also saw that at large Mach numbers, beta approaches theta, it is very close to theta. Explicitly if we take the limit that gamma goes to 1, then beta will be equal to theta, and 4 by gamma plus 1 will become equal to 2. So, even if we consider a thin shock layer, we are able to see that whatever Newton was predicting in hypersonic flows in the limit of large Mach numbers, we are very close to it. So, Newtonian methods to estimate quickly estimate the aerodynamic forces is used effectively in hypersonic flows. It is an estimate to start with, and later more refined theories can be used. For example, if you consider a flat plate at an angle of attack alpha, then we can find what is the force on this plate. The region behind the flow, that is the shadow region, this is shadow region, that has 0 pressure, that is what is taken. Or rather Cp is very low, it can be considered as 0, while only Cp is considered for the windward facing flow where the impact takes place, where at this lower half it is 2 sine square alpha. Therefore, the normal coefficient of force can be easily calculated. It is nothing but integration of the difference in pressures over the chord. Okay, so it becomes Cn becomes 2 sine square alpha. Now lift and drag can be calculated, they are components of this particular normal force. The lift is Cn cos alpha, drag is Cn sin alpha, therefore you get lift and drag of this kind. Finally, L by D ratio is also can be found, it goes as cot alpha. So these are the plots of CL, CD and L by D for the vehicle. So now if it is completely placed at 90 degree, then all the force is just drag, and we get CD in that case should be 2.0, which is what is coming over here. Okay, so it comes out to be 2.0, while CL gradually decreases down to 0, while L by D occurs at a maximum at an in between point over here. Okay, so you can apply these Newtonian methods. Later there was corrections done to the Newtonian, it was from approximate methods. So the correction was that there is a stagnation pressure that occurs at any body. So the reference pressure or reference Cp can be taken to be the stagnation pressure here at the nose, which is Cp max. Therefore Cp is written as Cp max by sine square theta. So this is plotted. Cp max can be found out from normal shock relations, because at the stagnation point it is a normal shock, and therefore if one plots using Newtonian methods, straight Newtonian without any modification is the upper curve, while the modified Newtonian is much closer to more exact evaluations using numerical techniques of a flow over certain shape body. So modified Newtonian gives a improved estimate of the coefficient of pressure. So with these discussions, what one must understand is while physical flow features in hypersonic flow become quite complex, very fact of high Mach numbers allows certain simplicity and to be done, and surface inclination methods like Newtonian are quite useful in estimating the coefficient of pressure. So this is a fact that we have been while discussing the oblique shock relations, also we have noted that if we non-dimensionalize the variables appropriately, like coefficient of pressure, CL, CD, or rho 2 by rho 1 or P2 appropriately non-dimensionalized by rho infinity square, they all become independent of Mach number. So P2 bar here it is represented as P2 bar is a normalized pressure. Similarly, rho 2 bar is normalized density, U2 bar and P2 bar are normalized velocities. We find that as the Mach numbers go to large values, normalized pressures, densities and velocities, they become independent of Mach number. This is known as Mach number independence principle. So from this we have an idea that in hypersonic limit, Mach number really does not play a major role. so the flow becomes somewhat independent of Mach number. So if you look at the hypersonic flows, a brief introduction that has been done over here, we have considered an introduction into physical aspects of hypersonic flows. Then there we discussed the complexities that arises, like high temperature effects, thick boundary layers and so on, thin shock layers, and as a result of say thin shock layers, high Mach numbers, certain simplifications are possible in the analysis of hypersonic flows. First, estimates of say aerodynamic coefficients can be evaluated based on simple local surface inclination theory like Newtonian theory or modified Newtonian theory. If we apply the limit of high Mach numbers to oblique shock relations in hypersonic flows, we see that a certain independence of Mach number is achieved in normalized values. With this, the area of hypersonic flows itself is quite vast, involving various aspects related to heat transfer effects, viscous effects and high temperature effects and so on, which is difficult to cover in such a short time. But this short lectures were to give an introduction to this topic, so that if anyone is interested, they can further pursue them. With this, we close on hypersonic flows, but we look at some other interesting aspects related to shock interactions and shock wave boundary layer interactions in the coming classes. Okay, thank you.